So this is a short discussion on the material in section 6.2, area between two curves or maybe more than two curves. And um, so to some degree, what you're going to be doing is just using material from the last, what we've learned in chapter 5, evaluating a definite integral. I think what makes this material in 6.2, 6.3, and 6.4 challenging is just your ability to visualize what the area that, or the volume that we're trying to calculate. So the volumes are in 6.3 and 6.4. 6.2 is area. Okay, so up to now, we learned the area between, we evaluated the area between a curve and the x-axis. So all we needed to know was the limits of integration. We knew that the area, the one side of the area was bounded by the line y equals 0, or the x-axis. So, but now it's going to be a little bit different. And so what we're going to do is just subtract two functions. So if I want to know the area, let's say between the graph of, like here, let me just make this a little bit bigger if I can. So like here, we have these two graphs here, y equals f of x, y equals g of x, and we want to know all this area here. So you see that there's like a bar there, that rectangle that's shaded in yellow. And I want to know all the area in between those two curves from A to B. So it's also bounded by the lines x equal A and x equals B. And so you have to basically, make that, but you have to graph that and understand what it is that you're trying, what area that we're trying to calculate. And so basically, yeah, you just take the integral from A to B and you subtract f of x minus g of x, and that'll give us this whole yellow rectangle right there. And we're just, the Riemann sums, you just set up all the rectangles. Okay, we're not actually calculating with Riemann sums. We're going to do definite integrals and use the fundamental theorem of calculus. Okay, so what's new that we didn't do before is that we can find the area bounded between a curve and the y-axis. So in this case, the independent variable is y, and the dependent variable is x. And so yeah, you'd be yeah. So now here, the curve, we want to find the area bounded between g of y and f of y, and also the lines y equals d and y equals c. And then you just integrate from c to d. It's just like integrating, along the x-axis, except we're integrating along the y-axis. So let's just look at a couple of examples, perhaps. And so we're just going to set up the integrals and not actually, I think calculating, that we've done that before. Though, a lot of the problems in MyLab and also in the quizzes, you will have to calculate the areas, but we've talked about that before. I think the new thing is just set up the integrals. Okay, so we want to find, so this wording here might be a little bit different because you see, a bunch of curves there. Y equals x squared plus 2, y equals minus x, and then x equals 0 and x equals 1. Yeah, so that's just, those are just x equals 0, x equals 1. Those are just vertical lines. And so you see the graph right there, right here. Here's your graph right there, and the areas. And so y equals x squared plus 1. Well, we know that's a parabola, and the vertex is 0, 2. Line y equals minus x. So it's kind of a well-known graph, right? It's just that straight line that goes down through the 0, 0, slope -1. And then x equals 0, that's the y-axis, and then x equals 1, it's a little bit further out here. And so then we see the area there. So in this case, this is one of the easier ones that we're going to do. It's the integral from 0 to 1. And so the higher function, the one that's above, is x squared plus 1. So it's x squared plus 1, and then subtract off the lower function, which is y equals minus x. So here's the upper function, there's the lower function. So we're ending up, and also remember the integral of minus x from 0 to 1, that's negative. So you're subtracting a negative number. Okay, so the total area turns out to be, x squared plus 2 minus the opposite of x. And so you're integrating x squared plus x plus 2 from 0 to 1. Okay, so here's another one. So here we don't actually have, we're not told the vertical lines. So, we're not bounding the area with vertical lines. Instead, we just have the parabola y equals x squared and the line 6 minus x. So what you have to do in this case, now you actually have to find out where these two lines intersect. I'm sorry, where these two curves intersect. And so you just solve this equation right here. So you have to find the x coordinates. You have to find the x coordinate of this point here and the x coordinate of that point there. And so you just solve the equation x squared equals 6x minus 1. Yeah, you get that. You get the quadratic equation x squared plus x minus 6 equals 0. And yeah, so it's kind of, this one was kind of set up easy. So the solutions are easy. Minus 3 to 2. Okay, so the function the higher function is 6 minus x. The lower function is x squared. So it's 6 minus x, and you subtract off x squared. And then we had to calculate the limits of integration. They weren't given to us like in the previous problem. So it's -3. So we're integrating from -3 to 2. Okay, and so I think that we know how to do that, do that integral. Okay, so here's another one. Okay, so now here's the first time we've seen where we're going to integrate along the y-axis. So in this case, we want the area bounded by the curve y equals minus x. Okay, I mean, not y equals minus x, it's x equals minus y. And now again, y is the independent variable and x is the dependent variable. So, and then x equals 2y minus y squared. And when you graph it, it looks like this. Now, students, if you have a hard time, because it's kind of new, we're not used to y being the independent variable, just change the role of x and y and just get an idea of what the graph looks like. Now, we still have to go, integrate along the y-axis, but if you're just having a hard time, so let's say, this is what I used, if it helps, let's say we're going to graph y equals minus x and y equals 2x minus x squared. The graph would look kind of crummy graph right here, but doing freehand, it would look something like this. And then that would be 3 comma -3, and that would be 0 comma 0. Okay, so when you interchange the role of x and y, the graphs are symmetric about the line y equal x. Okay, but that might just give you an idea of what the area, the area looks like, or the function looks like. Okay, but let's go back. So remember, this is just a suggestion. You don't have to do that. If you're having a hard time just visualizing what the graphs look like and what the area looks like, first, just change the role of x and y and graph and get that graph. And see, that'll just give you a rough idea. But just remember, the graph, when we interchange the role of x and y, the graphs are symmetric about the line y equal x. Okay, so here we get this. So the graph of x equals 2y minus y squared. Yeah, we're going along the y-axis here. So it's a parabola, and so we go up. This is kind of, it's positive y. It's just like when we go positive x. And then we have the line y equal minus x. And again, we have to find out where those curves intersect to get the limits of integration. Okay, and it turns out, well, we solve 2y minus y squared equals minus y. Once again, we get this quadratic equation, y squared minus 3y equals 0. So it's so the points of intersection are y equals 0 right here, and y equals but y equals 3. And and then that would be, yeah, and then you get, yeah, so when y equals 3, the x equals 0. Okay, so and then we just subtract off. So in this case, this might have the parabola is above the line y equal minus x, so we just subtract y times 2y times 2 minus y, subtract off minus x, and the limits of integration are from 0 to 3. So those are the 3 problems that I'm going to go over from the notes. And then I kind of encourage you to maybe look at the rest of this, or certainly look at the material in the book. But let's just try a couple of problems I selected from the homework. Is this the one I want? Hello. Okay, this is the one I want to look at first. So let's look at this one. I think it's problem number 6. And so here we want to find it's this area, we want that shaded in region. So of course now the graph's really nice because it's generated by MyLab. And wait, I went the whole way. That's not what I wanted to do. Okay, let's see if I can make this. Let's see. Okay, so let me go before I ruin this anymore. Okay, let's just keep it 125%. Let me try it one more time. What happens there? Okay, 150%. Okay, so we see we have the graph of the blue graph is y equals it's y equals 28 minus sine of x. And then we have y equals, the red graph is y equals 28 cosine of x. And we want the area bounded by those two curves and the line y equal 0. And so in this case, we're a little bit different than what we did before. Break it up into two parts. First, and when the graphs intersect at pi over 4, because I know that sine of x, I know that sine of pi over 4 is the same as cosine of pi over 4. So I know that, just from my knowledge of, or our knowledge of, not mine, just not mine, all of us, we know that our knowledge of trigonometry, we know those graphs intersect at x equals pi over 4. And so let's just first integrate y, the blue graph, y equals 28 sine of x from 0 to pi over 4. And then that'll give us this area 1 here. And then the area 2 is the integral from pi over 4 to pi over 2 of 28 cosine of x. And we just integrate those, just using, you can see I did all the steps there, that just using the fundamental theorem of calculus. Yeah, so we get, just get the antiderivatives, and then, it's the upper limit, evaluate the antiderivative at the upper limit and subtract off the lower limit. So that's kind of a, the reason I show this, I didn't see it, we didn't have an example like this in the notes. I do think there's a few of these in MyLab. Now, the other way we could have done it is, and here's my kind of crummy graph right here, but we could have subtracted off, right? We could have integrated along the y-axis here. Let me see if I can do this. And so, but what you'd have to do is, y would have to be the independent variable, and x would have to be the dependent variable. So so in this case, the x's would be in terms of, x would be, let's see, like for the top graph here. What would you get? X is equal to arc sine of y over 28. If you did it this way, yeah. And then the lower, and then that's the blue graph, and then the red graph would be arc sine of cosine over 28. And in that case, you would only have to, you would have to break it up into two parts, right? Because you'd be integrating along the y-axis. The only thing is, right now we don't know how to integrate the arc sine and the arc cosine functions. So that -1 there means arc cosine. I mean arc sine. Let's see. Okay, so we don't know how to do. You're going to learn how to do that, I think, and you should learn how to do that in Calc 2. So for right now, we're just going to integrate along the x-axis, and in that case, we have to break it up into two parts. But I think this is a pretty straightforward problem. You just have to recognize it has to be broken up into two parts. It can't just be one integral. So that's the trick here. So integrate under the blue curve from 0 to pi over 4, and integrate under the red curve from pi over 4 to pi over 2. Now the second problem here. Okay, so let's see if I can make this a little bit bigger. Hello. Okay, so now what we have here, we want to determine the area of the shaded region. So now we actually have, so once again, y is, so we're going to do it two ways here. We're going to integrate along the x-axis, and we're going to integrate along the y-axis. So the x-axis is a little bit harder. So one thing we're going to have to realize, and I'm going to show you this below. So we're going to break it down into two parts here. So there's that, see that line I just drew right there? And so we're going to integrate that. We're going to calculate that area, and then we're going to calculate the area on each side of that line right there. Okay, so so let's just first find the points of intersection. So we have the line y equal x, or x equals y, I'm sorry, y is the independent variable. And we have the curve x equals y squared minus 6. Yeah, so we get this parabola going along the y-axis. So let's see, what are so again, it's kind of set up nice to get the points of intersection. So we just solve y equals y squared minus 6. We get that parabola. It's quadratic equation. Y squared minus y minus 6 is 0. We get the points of intersection are y equal 3, and then also y equals minus 2. Okay, so and so now let's first the first part here. And I took a lot of pages here to, oh yeah, see here, we're going to calculate the red area and the blue area. And the thing to notice is kind of a coming attraction here. If we look at this blue, what is the red area, the area above the area above the x-axis, even though it may not look like that from my drawing, the area above the x-axis is equal to the area below the x-axis. So let's solve for, so let's make x the y. So let's make x the, so here's our original function. So now we're going to make x the independent variable and y the dependent variable. Okay, so we just solve for y. We get y squared equals x plus 6. And then when you solve for y, you get y is equal to plus or minus the square root of 6. Right, so the area above, this is what I'm saying. So we look at area 1. The area above is y equals the square root of x plus 6. And then the area below is y equals minus the square root of x plus 6. I'm doing my best to draw that freehand with my screen in a vertical position. Okay, but you can see that for any given x, you're going up, you're going up, the distance from the axis going up is the same as the distance going down. So like if x is 3, you're going up. So if x is 3, right, you'd be taking the square root of 9. So you'd be going up 3 and you'd be going down 3. So it's symmetric about the line y equals 0, the x-axis. So the area above the x-axis for area 1, remember, is this shaded in region there? So the area above the x-axis is the same as the area below the x-axis. So, and we know it intersects, did I say where it intersects the y? Yeah, and it intersects, I should have pointed out earlier, this peak here, that vertex there is -6, 0, right? Yeah, so when y is 0, x is net, right? All you got to do is plug in 0 in there. So you get the x-intercept is -6, 0. So you can integrate from -6 to -2, right? So remember, we also solve for where do the lines intersect. So this is this is the line x equals 2, this line right here, what I'm kind of shading in right there. So we're going to integrate from -6 to -2, and so we're going to get the integral from -6 to -2, and it's going to be the square root of x plus 6. Oh, I should have put a dx here. Okay, and it's twice, right? And the 2 is because it's the area, we're looking at the area above. Look at the area above, we're looking at the area below. So this integral just gives us the area above. So you multiply it by 2 to get the area below. So that's area 1, and now we actually have to get the other area, the blue area. And now it's just, we just subtract functions right here. So area 2 is bounded by the curves x equals 2, x equals -2, y equals x, and y equals the square root of x plus 6. Because remember, we're writing the, we rewrote our original function so that x is the independent variable. So, so here's x equals, so this is area 2. So that, remember, the area 1 and area 2 were separated by the line x equals -2. Okay, so so the upper part is y equals the square root of x plus 2. This lower curve here is the line y equals x, and this point here, we at the beginning we found that the points of intersection were 3, 3. Okay, so we're going to integrate. So the area 2 is just the integral from -2 to 3 of the square root of x minus x. So the total area is 2 times, if we're integrating along the x-axis, it's 2 times the integral from -6 to 2 of the square root of x dx, plus the integral from -2 to 3 of the square root of x minus x dx. So that's the first part of the problem. Okay, so the second part of the problem, okay, now we're going to integrate along the y-axis. So let's go back. So it's kind of hard to see because I've taken so many pages. Let's go back. Let's see if we can go back to the original function right here. Yeah, and so so in this case, yeah, so we're going to integrate. So the upper part is, so we have this curve x equals y, and we have the curve x equals y squared minus 6. So let's go back down here. Yeah, so in this, let's see if I can kind of vaguely draw it. Something like this. Probably not such a great drawing, but you can see, yeah. So x, yeah, so the y is it's going to be y minus x y. So this would be x. Let me try that again. It looks like a y. Sorry, the font changed, but okay, whatever. Okay, so so it's going to be y minus the parabola y squared minus 6. And remember the limits in this case. We have to look at the we have to look at the intercepts are given by the y coordinate. So once again, it's from -2 to 3. Remember, this was 3, 3. And then the y coordinate was -2. Remember, we solved for that way up here. Wait, sorry, it's kind of going back and forth, up and down. Probably isn't, makes it a little bit hard to follow. But yeah, remember the points of intersection of those two curves were 3, 3 and -2, -2. So we're integrating along the y-axis from -2 to 3. So when we integrate along the y-axis, we just have, it's just one integral. And so it turns out to be y minus y squared minus 6 from -2 to 3. So if you actually evaluate it, yeah, you get y squared over 2 minus y cubed over 3 and then the minus you get plus 6, so it's 6y. And then we just evaluate it at the endpoints. It turns out to be about 20.833. So I have this file online, so it might be easier for you to, if you're actually looking at this video, to have the file open on your own computer as well. Or to view it later. I guess you can't look at the video and look at the file at the same time. So that's all.